Hello algorithmicians, in this video I'm going to go through all of the ADTs that you met in Unit 3 and we're going to consider their time complexity. I don't think we're often going to be asked to do this in an exam situation because you'll see there is some ambiguity, but it has been asked before, and it's also very useful when you're writing your SAT project. So here we go. We're going to be covering lists, sets, dictionaries, arrays, stacks, queues and priority queues. So, arrays and dictionaries, these actually work in pretty much the same way. If we have an array, we might reserve a stack of memory. This is memory on the right hand side, and we will have our memory reserved for a particular array, and we'll have some kind of function which maps the number 0 to the first one, 1 to the second one, 2 to this one, and so on, all the way down. So here we go. Look up, and this takes us into our memory. So let's think about the functions we might want to do. We might want to access a particular item. What this does, it takes the item you want. Let's say you're looking for the third item. It puts it into the lookup function. That tells it it's 01003. I just made up these nonsensical memory addresses, and it tells us it is here. So that's done in constant time. I didn't have to look through all of the results trying to find number 3. So accessing it is going to be order 1. And a lot of things with arrays are going to be order 1. If we want to access or delete a particular item, anything that requires looking up by index are all going to be order 1. The only things that might not be order 1 is if we're doing something by value. So we could think of these operations as being split into index based or value based. So for example, if we want to find the word cat in here and we don't know where it is, we have to cycle through every item in the array. So that is going to be order n because we have to look potentially at every single item. If we wanted to insert and shift down, let's say we want to insert something, so we've got cat, dog, and we want to insert something here, well, we would have to move this one down, move this one down, move this one down, and so on. And the worst case there, if we'd be inserting something at the very top, so we'd have to shift down all of those items. So arrays are very efficient. One of the downsides is that you have to reserve that entire set of memory that you think you might need, and we can't easily expand the memory for the array when we're dealing with our level of algorithmics. Dictionaries actually work in the same way. Now in Python, dictionaries don't have a limitation for that you don't have to set the size in the first place. So a dictionary works by taking a key, and the way the key works, it takes a word like, let's say we're looking up, let's say we got a dictionary and it's got names, and a name maps to a phone number, something like that. So the name is going to go through what's called a hashing function, some magical function which converts it into a number. So instead of the lookup function, I guess this is a hashing function here. So we take the name, don't want to do that there, we might take the name Steve, hash that, that gives us a memory address, and that takes us to a particular particular memory address. Some stuff with hashing functions we don't need to know about for VCE algorithmics, like what happens if two of the same word map to the same address, and things about space complexity we're not too worried about. But that's why you can consider the time complexity of arrays and dictionaries in very much the same way. Next one we'll look at is sets. These are a very easily forgettable ADT, I think. A set contains elements, and it's just a way of checking to see if an item is in a particular set. So for example, we might maintain a list of members and we just want to see for a particular name, is that person a member of our club? It works a little bit like a dictionary. So we would take a name like Steve, that would go through a hashing function, which would go to a particular memory address, and in that function we would just either store Steve, or we might just store tick. We say it's present. So it doesn't hash to another value, it hashes to confirm that that thing is there. And so a lot of the same time complexities apply. If we want to add something to the set, we're just applying the hash function, takes us to a memory address, so that is order 1. Same thing if we want to delete, because we're essentially looking up, and well, that really means that then looking up to confirm if somebody is in the set is also big O of 1. So sets are simple, but they are very fast. There are some other operations you might see. So for example, we might have two sets, A and B, and we might want to find the union of those two sets. And in that case, we would have to go through every element in each list, check to see if it's not already in the new set, and if it isn't, add it to the new set. So again, because we're going through each element once, it's going to be big O of n. So that is the union operation. I don't think that's going to come up, but there it is just in case. Now, lists, they're not really well defined in the algorithmics course, which is kind of annoying because we can have two different ways of storing lists from the computer's point of view. The first is an array, and if it's an array, essentially the list is just an array which doesn't have a fixed size. So all the time complexities are the same. It's just you look up things by index. If you're searching for something, it's going to then be big O of n. Looking up by index is constant time. There is something called a linked list, and the way that might work, we might say the head of the list. So let's say we've got a list of names of people. So we might define our list, which is called names, and we'd have a pointer to the first memory address for our list. That goes here. And then we'd have the first person. Don't know why I'm fond of Steve today. And that might contain two things. It might contain Steve, and then it might tell us where is the next person. Now it's logical that that would be in 1002, but maybe not. One could be in 1006. So then we would go here. Just depends which memory address is free. That gives us Mary. Then that might point to 1009. So that will go to this one. And this will be, I can't think of any other names. Let's go Adam. And then eventually we would have an end pointer. So if this was the case, if we want to look up something by index, we can't just go straight to the third item in the list. So if we're accessing something by index, we have to go, right, here's the first one, Steve, that's number 1. The next one is Mary, that's number 2. Third one is Adam. So the worst case is we actually have to go through the entire list. If we wanted to search, that is going to be big O of n. It would have been anyway, because we have to look at every item to see if that item is the thing we are looking for. If we wanted to insert at the end, that is going to be big O of n. If we wanted to insert at the start, that's not going to be. That's going to be easier because that is going to be constant time. The way that would work, I would add another person. So maybe we would say we want to add Alia at the start of the list. Alia is then going to link to Steve, who is here. We put this, so that pointer is taking us up to here, and then we would change this pointer for the header of the list, which takes us to 100C. So that operation can be done in constant time. Okay. If we wanted to insert at any point in the list, like let's say in the middle, essentially that's linear time because we have to cycle through everything. So, and you can work out other time complexities for this list by considering the way it's linked together. But again, because in Python we use array-based lists, and I don't think the study design has made it super clear as to which kind of list we're talking about. I don't think this is going to come up. But if it did, and you wanted to justify why you've said it's a particular thing, you could mention that you're working on a linked list or an array-based list and justify your time complexity. Or if it was multiple choice and you couldn't work out why they thought accessing an item was in linear time, this could explain why that's the case. Okay, now on to some slightly harder ones. If we consider a stack, we need to have the name for our stack. So what should we call it? Oh, feeling unimaginative, we'll call it my stack. And we would have the first item, which might be, let's put it at the first item in my list. So that will go to here. And whether we have the linked list or the array based, well, we'll go for the linked list here. So we've got A, 1002, B, so that links to the next one. I'll just make this simpler. So for the stack, hopefully you can start to think through. If we want to insert something, well, that is just going to be done in constant time because we change this pointer to point to a different thing. So we're going to add something else, which is going to then link to first one here. If we want to peek, then that is, we've got to change that pointer, 04. If we want to peek, well, that is clearly, we're just looking at the address that's there for us. If we want to pop, I feel at this point it's worth pointing out, pop does not return something like it does in Python, it just removes the item. That's the opposite of insert. We go to the first, so as the thing is now, we would go to that address 1004, we'd read this thing here, and we would change the first pointer to that one. We wouldn't even need to delete that. That can just be sat there in limbo. So that is going to be big O of 1. Next, we will consider a queue. For the myQueue, the most efficient thing to do is store both the first and the last. So now, if we want to insert something, let's say we want to insert F, we take our last thing here, we change that marker to another memory address, we insert it at that memory address, and we update this one to that last item. So that is going to be done in constant time. If we wanted to dequeue, that is also going to be done in constant time with this implementation. We look up the first item, which is here. We change the marker to 1002, and then we can essentially discard that. So dequeuing is big O of 1 as well. The last one we're going to look at is very, very casual. You're not going to, I don't think, be asked to describe this, but a lot of people wanted to do it in their SAT. So there's different ways of storing a priority queue, and this way, what I'm going to describe here is a binary heap. So I'm not going into the queue nature of this, just the way that we might store a queue. And the way it has to work, each parent can have 0, 1, or 2 children, and the parent must be, in this case, smaller than both of its children. So 4 and 6, and then 7 and 5, and then this might be 8 and 9. So now, if I want to insert something, I would go to the bottom, I might insert it here, and then we do what's called bubbling up. So I'm going to compare my new child with the parent, and I can see here that they need to be switched. So I've got 3 and 7. I compare the 3 with its parent, so I can see I need to switch that. So we have 3 and 4. And now what we can see is that all of the parents are smaller than the children, and everything's fine again. What we do if we want to dequeue something, we remove the thing at the very top. We take the most unbalanced item from the bottom, which I'm not explaining properly, it's just for a flavour. And now we bubble down. So we compare 7 with its 2 children. We need the parent to be smaller. It's not, so we replace it with its smallest child, or switch it with its smallest child, which is 3. Now we look at the 7. Is 7 smaller than these two? No, it's not, so we switch it for its smallest child. We have 4 and 7. And once again, we are back to having our tree, which is balanced and has that loop invariant, which is that parents are always smaller than their children. Okay, hopefully this has been helpful for you to see some time complexities of ADTs for VCE algorithmics, and also to revise some of those ADTs and what they are.